Okay, so suppose now we would like to find the Maclaurin series for cosine of x. There are two options. One option would be to do everything that we did for sine x, to compute derivatives of cosine x, to find the Maclaurin series, and then show that it converges indeed to cosine. Or, and what we exactly are going to do is to differentiate this power series for sine x term by term. So we will differentiate the series for sine x. So let us take this equality. We have sine x equals to this infinite power series and differentiate it. So we know that differentiation of power series does not change the radius of convergence. So we'll still have a power series convergent for all x. It will still have radius of convergence equal to plus infinity. So differentiating this equality, we have the derivative of sine x on the left. So simply the cosine x on the left equals, now we would like to differentiate this term by term. So let's see what we will have here. We must write the derivative of this expression. So let us just do it this way. Just write the series over 2k plus 1 factorial, and then slap the prime on it. So this derivative is equal to the sum of derivatives of individual terms, which are the following. So we have minus 1 to the k, it is a constant, it does not change under differentiation, multiplied by, now we need to take derivative of this expression. Well, we're differentiating with respect to x, so 2k plus 1 factorial is a constant. As a constant factor, it will remain unchanged. And for the x to the 2k plus 1, we differentiate it as a power function. So we multiply it by the exponent and lower the power by 1. So this is the derivative of the kth term of the power series for sine x. Let us simplify it now. So we see that it is equal to the sum. Now what can we simplify? Of course, we have 2k plus 1 on the top and 2k plus 1 factorial over here. So we must recall, therefore, that 2k plus 1 factorial is 2k factorial multiplied by 2k plus 1. Right? This is effectively the same as saying that n plus 1 factorial is equal to n factorial times n plus 1. This is the exact same equality, with n being 2k. And so we have -1 to the k, then 2k plus 1, x to the k, x to the 2k on top, and 2k factorial times 2k plus 1. There is cancellation. And the final expression that we obtain is the sum k from 0 to infinity, -1 to the k, x to the 2k divided by 2k factorial. And this is the representation that we obtain for cosine x. Now, there are a couple of things to observe here. First, this representation holds for all x. In other words, the radius of convergence of the series on the right is infinite, because the original series that we differentiated had infinite radius of convergence. The same will apply to the result of this differentiation. Secondly, it is interesting to notice that on the left we have an even function, right? So cosine x is even, meaning that cosine of minus x is the same as cosine x. And indeed on the right we have a power series which only contains even powers of x. So the right hand side is also even. And if we were to look into the first several terms of this series, we would see that it starts off like so. For k equal to 0, we have 1 over here, and x to the 0th degree, which is 1, divided by 0 factorial, which we have agreed to be equal to 1 as well. So we simply have 1. Then minus, for k equal to 1, I have -1. And then x squared divided by 2 factorial plus x to the 4th divided by 4 factorial minus x to the 6th divided by 6 factorial, and so on. So the signs of the terms here are alternating, and we're only summing up over even powers of x. And this gives us the representation of cosine x as a power series in a very straightforward way. So we did not have to go through the computation of derivatives, we did not have to show equality, because everything was immediately implied by the fact that we could differentiate the series for sine x term by term. And all of these properties, we got them for free.